This last video, we're going to be talking about how we might measure cardiac function, and then we will also talk about things that might regulate this cardiac function. So when we think about cardiac function, we're thinking about how much blood it's pumping, right? Your heart's a pump, and we can measure it based on how much it can pump. What's the volume it can pump? A lot of this measurement is done using what's known as echocardiology. It's actually a sonogram that measures the volume within the heart. And what it does is it actually will measure the volume in a ventricle just before it ejects blood, and then just after it ejects blood. So you can measure how much was there kind of when it was full. So you can measure that end diastolic volume. And then you can measure it again after it ejected and get the end systolic volume. Then you do a little math and you can determine what's known as stroke volume. So stroke volume is when you know what you started with, that end diastolic volume, that's the full. You know how much was left behind. So if you subtract what was left behind from what was there when it was full, you'll get how much was ejected from the ventricle, okay? And that's known as stroke volume. Now, we can also take these numbers and look at them slightly differently, and that's known as the ejection fraction. So we're basically using the same numbers, all right, these three volumes, and we're determining the percent that was ejected. So a percentage is typically when you take part of a volume and divide it by the whole volume. So we're taking how much was ejected, that's stroke volume, divided by the end diastolic volume, how much was there before it ejected, and you get a percentage. All right, you do the division, you multiply by 100 to get the percentage. So what ejection fraction means is what percentage of the end diastolic volume was pumped out. All right, so what fraction was pumped out. And during rest, a normal heart's at somewhere around 55%. So what that means is, it doesn't eject 100%. We already know that, but it ejects about just over half the volume when it's full. Now, when you start exercising, that percent can go up. All right, so you can actually eject more stroke volume if necessary. So this is kind of a good indicator of how well that heart is working, kind of during normal resting activities. They also might do this during a stress test. So they might have the individual walk on a treadmill, or they might give them epinephrine to get the heart beating faster and harder, and see, what percent, at maximum maybe exercise is that heart ejecting. All right, another measurement, and this is probably the most important measurement for us to know, is called cardiac output. So cardiac output now is measuring the volume, but not in one beat, right? Stroke volume is just one beat. We're looking at the volume that heart is pumping over a minute, all right? So to determine what it pumps over a minute, you have to know how many times it beats per minute. So you have to have knowledge of the heart rate, okay? So now we're taking the stroke volume, which again, that's just one beat. We're multiplying it by the heart rate, so how many times does it beat per minute, and we get the cardiac output, the volume of blood ejected each minute. If we use some numbers, for example, the numbers we have been using was that 70 milliliters for stroke volume. A normal heart rate's about 60 to 75, so let's just take 75 as a normal heart rate. If you do the math, 70 times 75 is 5,250. Now that's in milliliters per minute. Now, typically we convert that. So cardiac output is almost always given in liters per minute. So you have to know how to convert from milliliters to liters. The easiest thing to do is just move the decimal place over 3 times, and you'll get liters per minute. All right, so that's about a normal average cardiac output at rest. In this case, an adult male. Female is going to be a little bit lower than that. And this happens to be about the same as normal blood volume. If you remember from the blood chapter, we learned that a normal male has about 5 to 6 liters. So what that means is the entire blood volume flows through the entire cardiovascular system in about a minute. All right, and that's at rest. Now, we could increase this. All right, so during intense exercise, right, what happens? Well, heart rate goes up, you know that, but so does stroke volume. So if you increase both stroke volume and heart rate, you can actually get that cardiac output up 4 or 5 times greater than it is at rest. So you could get it up over 20 liters per minute. The difference between these two numbers is what's often referred to as cardiac reserve. So you have kind of a 5 liter per minute at rest. You have, 20 liters per minute maximal. And then, the difference would be what you basically have on reserve. It's the volume you could potentially circulate if necessary. All right, so let's talk now. The rest of this PowerPoint's all about things that influence kind of cardiac output in the heart. This happens to be the nervous system. So this topic basically is, how does your nervous system regulate the heart? All right, so in the nervous system that is controlling your heart is the autonomic nervous system, okay? And all kind of neurological pathways you can think of as having an input. So what is the information that the brain needs? All right, what kind of information that's occurring in the body does the brain need to then analyze, all right, interpret, kind of integrate all this information, and then determine what the output should be, okay? And the output is going to be basically, what do we need to do as far as cardiac output is concerned? Do we need to increase the volume pumped per minute, or should we decrease it? So let's kind of go through this. This is all the normal input that your medulla oblongata gets. So this area here, called the cardiovascular center, is in the medulla oblongata. You should remember that from A&P 1, that the medulla has some vital control centers. It controls your breathing. It also controls your cardiovascular system. So what kind of information does it need? Well, it's going to get some from within the brain itself. So there's other things in your brain that might play a role in what your heart needs to do. Cerebral cortex plays a role. Limbic system, if you remember, the limbic system is your emotional brain. So emotions can influence what your heart's doing. The hypothalamus, that has to do with like body temperature. We're going to see later that body temperature does influence what your heart's doing. Then you have what's called peripheral. Peripheral means outside the brain. So we need to know whether we're moving or not, all right? Because if we're moving, we probably need to pump more blood. So that's done using proprioceptors. Proprioceptors are found in joints and muscles. And when these receptors are activated because you're moving, we send that information to the medulla. Chemistry is important. So for example, if you're low in oxygen, right, we probably should know that. So we can circulate more blood to the lungs in order to get more oxygen. And then blood pressure. Blood pressure is important because your heart can influence blood pressure. So let's say your blood pressure gets too low. Well, you can actually increase cardiac output in an effort to raise blood pressure. Or if your blood pressure is too high, you can decrease cardiac output. All right. So this is all what we would call input. All right. It uses sensory neurons, right, that send all this information to your medulla oblongata, or the cardiovascular control center, and then it determines what kind of output there should be. And if you recall, the autonomic nervous system is all about understanding sympathetic versus parasympathetic. We have what's called cardiac accelerator nerves. Those actually come out of the spinal cord. All right, so if you remember, the sympathetic division is also called the thoracolumbar division. And that's because the nerves come out of the thoracic spinal cord and the lumbar spinal cord. So there's nerves that come out of the spinal cord that are sympathetic, all right, and that's going to increase heart rate. So I would just this part here. So it can increase the heart rate. It can also increase what we call contractility. That's the force. So this should make sense because remember, when you're exercising, that's a sympathetic activity. So what happens when you exercise? Your heart rate goes up and your heart beats harder. All right, so now we're going to increase cardiac output, all right, using sympathetic stimulation. At rest, your sympathetic division is inhibited and your parasympathetic division is stimulated. So at rest, you have more activity in your vagus nerve. Now, your vagus nerve, if you remember, is a cranial nerve. So sympathetic activity comes directly out of your brain. Parasympathetic activity comes out of your brain in the vagus, and it is used to decrease heart rate. Okay? So this is a really important slide to understand, but it's a pretty straightforward question to ask yourself. Do I understand what the input is, where the control center is, and how sympathetic activity affects the heart, and how parasympathetic activity affects the heart? All right, this next figure talks of kind of the same idea, but it's looking a little closer at the blood pressure angle. All right, so this is going to introduce what's known as baroreceptors. Baro means pressure. So if you've ever heard, in climate and weather, we use barometers to measure the atmospheric pressure. These baroreceptors measure your blood pressure, and they're found in two very important locations. They are in the carotid arteries. All right, so this is a carotid artery that's found in your neck, and they're located in the aorta. So that's the two really important locations that your nervous system monitors your blood pressure. All right, whatever that pressure is, you're constantly telling the medulla. There's that medulla again. So it's interpreting that pressure. All right, so let's just say the pressure is too low. Something's causing your blood pressure to be too low. One example might be you're hemorrhaging blood. So you're bleeding. You're losing blood volume. And when you lose the volume in your bloodstream, your pressure goes down. I always think of like a garden hose. If you decrease the amount of water in a garden hose, that pressure in the hose goes down. If you increase the volume in that garden hose, the pressure goes up. So we have low pressure. We tell the medulla, all right, and in this case, the medulla is going to then use sympathetic activity, all right, so it's going to inhibit the parasympathetic. We don't want that. We want to raise the sympathetic activity. So this heart will beat faster. It'll beat stronger. All right. We also activate the adrenal glands. Remember, the adrenal glands are going to produce epinephrine and norepinephrine, which are in essence going to do the same thing as the sympathetic cardiac nerves. All right. And that'll raise your blood pressure. Now, if your blood pressure was too high, we want to reverse this. We want to turn off these sympathetic nerves. All right. And we want to activate the vagus nerve, and that'll slow that heart rate down in an effort to then lower the blood pressure. Okay? So this is called the baroreceptor reflex, where we use baroreceptors to monitor pressure. It's a reflex, all right? So it's an involuntary response that will either raise pressure by increasing cardiac output or lower pressure by increasing parasympathetic activity. This is a figure from your book. It's a little small on here. It's basically showing the same thing. At this point, I'm typically not going to walk through these figures because I think by now you could kind of go through this on your own. But remember, here we're either starting with high pressure, all right, and you would follow this upper part of the figure, or if our blood pressure is too low, we follow kind of this path. All right, so it's a basic example of homeostasis, in this case, blood pressure homeostasis. Okay, This figure's got some information that you're gonna. I know we've done a lot of videos on the heart, and it's not easy concepts, but this figure's gonna have quite a bit of information on it. But the idea is, what are all the things that'll influence cardiac output? All right, so notice that all these arrows eventually go to this purple block that says increasing cardiac output. All right, so this is kind of a review slide of a lot of the things we've been touching on here and there, but it kind of summarizes it all. So we can always work our way backwards. So we're looking at things that increase cardiac output. So what are things that'll increase how much blood your heart pumps over a minute? Now remember that what determines cardiac output is stroke volume and heart rate, right? So when you multiply these two together, you get this. So we're just then separating this figure out into all the things that might affect or increase stroke volume. And then on the bottom, what are the things that will increase heart rate? So let's start at the bottom first, heart rate. So think about things that you know already that increase your heart rate. Well, you should immediately think sympathetic activity, right? Fight or flight. So that's right here, increased sympathetic stimulation. At the same time, you're going to have increased sympathetic, you're going to have decreased parasympathetic, right? They're inversed. This is all that input that we already talked about. So we talked about this part already. What else? Other chemicals. So this is nervous system. Well, what are some other chemicals? Typically what we're thinking about here are hormones or other things that might be in your bloodstream. Catecholamines are epinephrine and norepinephrine. So, that's just a class of hormones, but you could probably cross that out and just think of epinephrine and norepinephrine, which we already know, right? That's adrenaline. It's, basically a way to do a lot of those fight or flight responses, but instead of using sympathetic neurons, we're using hormones, all right? Thyroid hormones increase heart rate, all right? So thyroid hormones have an effect on the heart. So if they speed the heart up, they could affect cardiac output. And then we've got calcium. All right, the more calcium there is available, the faster the heart will beat. All right, so calcium will influence heart rate. This third panel here is just other stuff. All right, so age affects heart rate. When infants or babies are born, their heart rate is much faster than the mom or a normal adult. So you're kind of born with a fast heart rate. It slows down, so your heart rate's probably the slowest when you're kind of a healthy young adult. And then as you age, it kind of starts to speed up again. So that's why they have infants and senior citizens, compared to an adult, tend to have faster heart rates. If we compare male versus female, females tend to have a slightly faster heart rate. Notice here, low physical fitness. So if you're very physically fit, if you're kind of an endurance athlete, you have a low heart rate. This is the opposite. If you're not very physically fit, your heart has to actually beat faster because your body's not as efficient as it is when you're an athlete. All right? And then here's the temperature angle. When your temperature goes up, your heart actually beats faster. One thing you might want to think about is how you remove heat is circulate more blood to your skin. So kind of in an effort to remove heat, your heart will beat faster. Okay, now we're looking at the top of this figure. The top of this figure focuses on stroke volume. So what are some things that will increase the volume that the heart will eject? One thing is called preload. So preload, the key word here to remember with preload is stretching. So if the heart stretches, now what would stretch the heart? More filling. All right, so basically the more blood that enters the heart, the faster it'll beat. All right, because it stretches. Okay, I'm sorry, not faster. The stronger it will contract. Okay, we're up here at kind of strength of contraction. So increasing the filling so you get more venous return. So if more blood enters the heart, it stretches, and then that results in a more forceful contraction. It's kind of like a rubber band. The more you stretch your rubber band, the more forcefully it recoils. So same idea. The more you stretch the heart, the more forcefully it contracts. All right, and this is known as Frank Starling's law of the heart. Okay. All right. The middle panel here is unrelated to stretch. So if it doesn't have to stretch more to beat harder. There are other things that'll tell it to beat harder. So these things are known as inotropics. So inotropics, anything that's classified as an inotropic agent, affects how forcefully the heart contracts. If you're positive inotropic, you increase force. If you're negative, you decrease force. All right, so contractility is force, but it's unrelated to stretching. So it's just, okay, disregard any kind of stretching. What might tell the heart to beat more forcefully? All right, so what tells your heart to beat harder? Sympathetic stimulation. We know that when you exercise, your heart beats harder. Those same catecholamines, epinephrine and norepinephrine, make your heart beat harder. Glucagon does, but we don't need to be that concerned about that right now. Thyroid does. So now someone who has hyperthyroidism will have a faster than normal heart rate, and it might be beating more forcefully because of those thyroid hormones. And then there's calcium again. So you'll notice a lot of the things up here that increase the force also increase the rate. Okay? If you affect the force, you're inotropic. If you affect the heart rate, we call you chronotropic. All right? Okay, so the third thing here I want to talk about up on the top, and then we'll kind of come back to heart rate again, is called afterload. So afterload is the pressure that the heart is up against, right? So what the heart has to work against is blood pressure, right? If your blood pressure goes up, the heart has to pump harder, right, to overcome that high pressure in your arteries. So notice that this is a decrease afterload will increase stroke volume. All right. So if your blood pressure is nice and low, all right, your heart actually can eject blood pretty efficiently. But if your blood pressure gets high, it makes it harder. So your heart will actually have a lower stroke volume if your blood pressure goes up. All right. So hypertension, which is high blood pressure, chronically high blood pressure, will increase afterload. All right. We don't like that. All right. That's making the heart have to work harder. We want to decrease afterload. We want a low, right? We don't want high blood pressure. We want a nice normal blood pressure. Okay. So that's known as afterload. It's basically the pressure that the heart is pushing the blood into. So it's the pressure in your arteries. And if that pressure goes down, we can eject more blood. But if that pressure goes up, it's harder to eject that same volume. Okay, so then the last thing I want to do, I didn't mention this when we were talking about heart rate, is another word we need to understand, chronotropic. So chrono means time, like chronology is the study of time. Heart rate is a time measurement, right? It's beats per minute. So if you're anything that affects the heart rate, so all these things down here, we call them chronotropic, all right? Now these things down here happen to increase heart rate, so they're called positive chronotropic, all right? If it's something that decreases heart rate, we would call that negative chronotropic. And we've talked about something that decreases heart rate. It's parasympathetic stimulation, right? The vagus nerve, right, which is parasympathetic, slows your heart rate. So the vagus nerve is considered negative chronotropic. All right? So make sure you understand the difference between inotropic, which is force, versus chronotropic, which is rate. And then positive means you increase, negative means you decrease. Okay, so that's a lot of information to take in. Now's the time just to let it process. All right, go over small topics at a time. But typically, the most important information is towards the end of these PowerPoints. So this physiology stuff, these last, 4 videos, really needs to be studied hard. And not all at once. Try to take it topic to topic. All right, best of luck. Let me know if there's anything I can help you with.